So the second talk is from Antonio Montalban, who is going to talk about determinacy within second-order arithmetic.
Thank you, Ludwig, and thank you to the organizers for the invitation to speak here. So I'll be talking about determinacy within second-order arithmetic. This is joint work with Richard Shore from long ago. So I gave last week when they told me to give a talk, I asked the organizers whether they wanted me to give a talk on some newer stuff but it's a bit more technical, or on this older stuff that I thought might be more interesting to the philosophers. And I don't know, but it might be. And Anna chose this topic. That's why I'm giving this talk that probably the math part of the audience have seen me give many years ago, but the other part of the audience I haven't. So that's why I guess there are a few things that I changed from older talk, some ideas for the proofs I have a time that maybe people haven't seen. But yeah, it's mostly a review from a couple papers that we did with Richard Shore some years ago. What is I'm not talking about? I just want to give a little progress report about the other topic that I'm not talking about. Just one slide. Because this is the transfinite Ramsey's theorem that we are working with Alberto Marcone. And since we both gave talks about this in the last year, so what is the progress report? I'm not going to go into details, it's just one slide. So we have a version of Ramsey's theorem for ordinals. The new thing, this is the new thing that we're looking at is that the exponents, the size of the tuples, is an ordinal. These are not transfinite tuples, these are finite sets of numbers, but in proof theory you have this notion of a finite set of numbers being gamma large. They're given fundamental sequences for ordinals below gamma, and those are the tuples of numbers that we're coloring. And then the rest is the usual Ramsey notation. I won't go into details, it's just that that's what we're doing. We're coloring gamma tuples instead of, and then we are also, and these are also finite sets. These are ordinals, the alpha and the beta that we have in Ramsey there, but these are finite sets that are alpha large or beta large, or those are ordinals. So that's the usual kind of Ramsey notation. And what we have is an almost a theorem. It went down from the last time that we talked. And it's essentially, I tell you why almost. We have that for all countable ordinals, alpha and gamma and beta, there exists an ordinal beta such that you have the Ramsey notation. This means finitely many colors, less than omega. This is the usual Ramsey theorem, but now with ordinal. And the interesting part is that we find the Ramsey number. Kind of what is the beta, the least beta that you can find given alpha and gamma. And this is our functions that proof theory is knowing about ordinals. This is the fields, the Veblen functions. Function has 120 years or something. The logarithm of omega is kind of the reverse of the Cantor-Lamarck form, kind of going backwards. And this is alpha times omega. So that's the interesting part, that we kind of find the Ramsey number. And then this has the reverse math and computability implications, because I don't know, the Veblen function up to some ordinal has to do with those many iterations of the Turing jump. And we do that in a previous paper with Alberto. We look at the computability, but the proof theory is no connections. So these things go beyond ACA naught and below ATR naught. The progress report is that we're still plowing through the details. So essentially, we met with Alberto before the pandemic in Berkeley. We got all the proofs. Oh, I have this theorem, it's wonderful. We got a few talks. Then say, okay, now let's write down details. And then there are a million details. Probably people in proof theory knew this already, but we didn't know that. That when we had to work with ordinal notations, like nothing is as we expect. So every little thing, oh no, this doesn't work, we need to fix it. Oh, this doesn't work, we need to fix it. But I think we're kind of fixing all the small details little by little. And it looks like we'll eventually get them all, right? Who knows? But
We are confident.
we are, yeah,
We are confident.
yes. But that's why it almost a theorem. But okay, so that's what I'm not talking about.
So you said rule in ATR? But stronger than?
Yes, that's rule in ATR, and then if you fix the gamma, then you're roughly at gamma jumps. If gamma is of the form omega to the something, that's something.
Of course, it all depends on the details.
Hmm?
The devil's in the details.
Yes. So that part about the jumps is probably correct. But then
There's lots of room when you're jumping.
there is a yes, yes, there's a lot of details because we're doing this these notions of beta large, alpha large for ordinals involve these ordinal notations and going down, and you're working with finite sets that represent the ordinals, and they behave somewhat like the ordinals, but not exactly. So.
Are these first order statements or second order statements?
For instance, if you fix ordinal notation for alpha and gamma, and then you have like this beta, you can take it from a long enough ordinal, like I don't know, gamma naught, then it's a first order statement. First order. These are all finite things, and then you have representations for the ordinals and stuff. This becomes first order. So then in that sense, yeah, you get something that is first order and is at the level of beyond ACN, or beyond PM. And you can stratify. This gamma lets you stratify results from PA to HNO. Okay, so what am I talking about? So I'm talking about this question. How much determinacy, this is the old topic, how much determinacy can we prove without using uncountable objects? Okay, so that's the question. So how much determinacy can be proved without using uncountable objects? Okay, so mathematics without uncountable logic. What is the actual question we are looking at? Like a mathematical question we're looking at. We're considering these two theories. Like CFC minus P is a CFC without the power set axiom. And second order arithmetic, you guys know what second order arithmetic is. They both prove the same pi14 statement. CFC minus and second order arithmetic prove the same pi14 statement. That's a theorem. So we prove it in the paper, but it's, we talked to Michael Rudgin and he figured out the pi14 in like 5 minutes. So people knew this. He was like, yeah, pi14. So it's a technique that they knew. The statements that we're looking at are pi13. So they fall within the conservativity. So for us, the question of how much determinacy can you prove is the same where you ask CFC minus and second order arithmetic. So the question is the question we're looking at is how much determinacy can you prove in those theories. I leave it to the philosophy to answer first to answer whether this is the same question or not. So they put this question kind of like just to motivate the other one, but the real question is the concrete question is how much determinacy can you prove in Z2, in second order arithmetic. Power set is kind of the first axiom that takes you to the uncountable. So in that sense, it's going to the uncountable. So from our standard axiomatization CFC, that's the one that takes you to the uncountable. So that would mean uncountable objects. But that's maybe this another way. And I always, when I look at that question, then I think, well, maybe in some other world, like determinacy is the natural thing. And determinacy is just second order statement. So if you're assuming determinacy, you don't need to assume like the uncountable sets exist. Okay, I'll leave you guys to discuss that later because I don't know what is it. Okay, so how much determinacy can you prove in second order arithmetic? Oh, one comment about this pi14. Yeah, sigma 15 is there's a sigma 15 statement that is provable in CFC minus and not in second order arithmetic, and is some version of choice, sigma 13 axiom of choice. So that's the boundary of conservatism. Okay. So since the talk is about determinacy, probably you guys know what it is. but since that's kind of the main topic, let me review what I mean by determinacy, because we get everybody on the same page. So we fix a set of sequences of natural numbers, and that set is going to determine a game. So from this array, we're going to get a game. The game is played as follows. We have two players, 1 and 2. They play numbers alternatively, and they play forever. When they are done, they end up with an infinite sequence of natural numbers. And if the sequence belongs to your original set, player 1 wins. If it belongs to the complement, player 2 wins. So each A determines a game. A strategy in a game is a function that tells you how to play, that tells some player how to play. So it's a function that, given the sequence of numbers played so far, tells you what to play next. So it's, if you have a strategy, you cannot follow in a rule to play. You don't need to think at every move, you have to follow the strategy. And a winning strategy is one that wins every time, doesn't matter what the opponent plays. So that's a winning strategy, just wins every single time. So it's one of these functions. A winning strategy for player 1, doesn't matter what player 2 plays, you always, if you follow the strategy, you win. That's a winning strategy. And we say that a game, or in this case, a game is determined by a set of sequences of natural numbers, is determined if one of the two players has a winning strategy. If there exists a function, there is a winning strategy for one of the two players. And if you have a class of sets of reals gamma, like open or sigma 03 or pi 04 gamma, then we're going to use this to denote the statement every set in A in gamma is determined. Which is a statement, second order arithmetic. Every set in gamma is determined. Okay, so if gamma is the open set, and open determinacy means every open set A is determined. Questions so far? Everybody's good with the basic definitions? Cool. Okay, so what is the a little bit of very early history of the study of determinacy? There is a lot of history after this. That is super interesting also, but this is the history that goes to the point that we want to look at. So, determinacy was introduced in that paper in Stewart in '53, and they proved that open determinacy is true, and they proved that full determinacy is false using choice. Very important use of choice in there. Since then, a few years later, Wolf and Davis proved G delta and F sigma delta determinacy. This one took 10 years to get to pi 03, took 10 years from pi 02. By then, they were already asking whether that's going to be able to extend that to Borel determinacy. Is Borel determinacy going to be true? In the 70s, Paris shows one more level, pi 04. And then Martin proves analytic determinacy. All sigma 1 sets are determined, but using actually, he used a measurable cardinal in the first proof, but then it was improved to sharps exist. But this is a hypothesis that is outside CFC. So it was telling you that things were going to work out, but we didn't know about CFC. So things were getting interesting. Harvey Freeman comes. These are the years of the papers. I don't know exactly when these things happened historically, but probably around the same time. Freeman proves that to prove pi 01 determinacy, you need to use the power set axiom. So you need an uncountable set. He proves that you need the necessity. And to prove Borel determinacy, you need Aleph-1 iterations of the power set axiom. Or alpha many for all countable alpha, essentially. So that, it really has some logical strength to prove determinacy, but it wasn't really known if it was true at all in CFC. But then that gives a hint to Martin that he needs to use power set axioms. And then he proves Borel determinacy in '75, so a huge theorem. when he does that. And this is, this is the early story. This continued. Projected determinacy was a whole story that came in the 80s and still winning set theory. But we're not gonna get that far. All right, so that was a pretty cool story of determinacy. Another reason that I find the study of determinacy interesting, it's that it gives us a natural spine of statements ordering logical strength. So an empirical observation is that the natural statements that mathematicians or logicians have looked at are well ordered and their consistency strengths. That's an empirical observation that I think is one of the most interesting, a very interesting observation in logic that we don't really know how to explain exactly. We don't know what natural statement means. I guess what is a natural statement? We recognize them when we see them, and they seem to behave like that. And understanding that, I think, is a pretty interesting endeavor. And in some contexts, some aspects of this phenomenon can be proved, like in the case of Martin's conjecture in the Turing degrees. It's a kind of, it's another way of, like this same observation, but in a different setting, kind of the same phenomenon in a different setting. Is Martin's conjecture that is says that the uniformly degree invariant functions from the reals to the reals, Turing degree invariant functions, are well ordered. When you compare them on a cone, I'm not going to go into details of what they are, but it's telling you that the complexity, these functions that give you complexity are well ordered. And though this can be proved to be true, at least in the uniform case, open in the non-uniform case, but I think those are two sides of the same coin. One thing that another one that can be proved, this is completely proved, is wage results, that the Borel sets of reals are well ordered and the wage reducibility. These are for classes of sets of reals, and these are actually well ordered. And again, it's another side of the same coin. The motto was, this is probably the question existed before, but she published it in a paper. So it's she has this kind of general programmatic question of take the classes in the wage hierarchy, which we know is well ordered, and look at the strengths of determinacy for the things on that class, and you will get, this is defining a natural spine of statements that are increasing in logical strength. And it so happens that this, when we look at this, I mean, a lot of this has been done. It is the same line as the natural statement that we look at in set theory and reverse math. We're going to see it's not the same statement. The stops, the milestones are not exactly the same, but the line seems to be the same. So we get into that. Okay, so that's another.
Isn't wage a little finer?
Wage finer than that result?
Well, finer than Turing.
Well, it's different. It's different because wage is for sets of reals and their continuous reducibility.
Right.
And that one, yeah, it's not exact. It's a different comparability that they are connected, I guess. But I would say one.
The Borel hierarchy. The wage hierarchy is finer than the Borel hierarchy.
Yeah. So in that, the Borel hierarchy is closer to, I guess, the Martin.
Yeah, so that's so it's
mean.
finer than the Borel hierarchy, which kind of is a dual of the Turing Borel in some sense.
Yes. Yes. Right. So between between sigma 01 and delta 02, you have the whole Ershoff hierarchy of sets in between. Up to Turing degree, they are the same, but in the wage hierarchy, you have a whole different collection.
Right, you have the same things in the wage, I think.
Like in the many one, it's similar to the many one. It's closer to the many one degrees than to the two. And actually, but then that gives you even more determinacy statements along the way, because you have all this difference hierarchy along the way to start. Okay, that's what I said. Determinacy along the wedge hierarchy provides a naturally defined spine of statements that I think is maybe also another statement that could be interesting to the philosophers or not. Okay, so here, I mean, with respect to that question, this is what was known. We don't have to go through all of this, but essentially, here are the classes of sets that we're looking at. We're looking at the strengths of determinacy for that class in the setting of reverse mathematics. And Steele, Tanaka, Metzalen, Welch, people have worked in this, and they got, these are, up to here, they are strict, they are exact reversals. For pi 03, Welch gets something that is not exact. It's provable in pi 13 comprehension, but not in delta 13 comprehension. Freeman's proof that pi 05 determinacy wasn't provable in second order arithmetic was improved by Tony Martin to pi 04. So here we get very close, pi 03 and pi 04 determinacy. That was kind of the limit, like where the difference, the jump to be outside of second order was before. Martin has a book on determinacy that he's been writing for like 30 years, and it's open. Anybody can make it. If you ask somebody who has it, I can give it to you. I can give it to you. The PDF. I don't think he's ever going to publish it. I hope he does.
Right? He retired.
Right. So.
Is he active? I don't think so.
Well, and I mean the book is almost written. But for instance, he had a mistake. He had claimed this. I wonder how many people had read that proof. So he had claimed that without the power set axiom, you could prove delta 4 determinacy. So in second order arithmetic, which will give you a sharp bound, because between delta 4 and pi 04, there is nothing in between in the wedge hierarchy. So delta 4 was beyond, delta 4 was within. So Richard and I guess Richard had the idea to work on Turing determinacy in reverse math, which we later did, many years later. So we are reading this book, and then being reverse mathematicians, we noticed that it was using more induction than it was. I guess probably being a set theorist, you didn't worry too much about induction. But we are more used to be worried about induction. And he was using induction on a predicate that to define it, you need the full satisfaction predicate for second order arithmetic. So you need like pi 1 omega predicate, and he was using induction on that. So now I think he's correct, and so now he fixed it, and now he says that, well, CFC minus implies delta 4 determinacy on omega models. And I think the proof works on omega models, but don't remember the details. On omega models is fine. So then we tried to see what we could prove with Richard. If that was wrong, what was correct? What was the limit? What is the line when you just had to go outside Z2? Okay, so let me just tell you the results from now, and then we'll discuss them later, but let's just show the results. And then we go into more details on them. So, okay, so first, essentially, this is the proof that's in Martin's book. We had to kind of worry about all the details, make sure they're working the right system. It took some work to write them correctly, but the ideas are essentially due to Martin. And is that in second order arithmetic, you can show, so given an n from beforehand, 74, you can show that every Boolean combination of 74 pi 03 sets is determined. And second order arithmetic can do that. But what's happened is that the largest the n, 74, if we move to 170, then you need more axioms. The larger the n, the more axioms are needed. And so then we can prove we could prove that C2 does not show that every Boolean combination of pi03 sets is determined. So we don't get, so if you put the given the n inside, C2 doesn't prove. So you need more and more axioms, you end up needing infinitely many axioms to prove that. Okay, so in particular we get that CFC without the power selection doesn't prove delta for determinacy, which Martin had claimed in the book. It doesn't even prove Boolean combinations of pi03. And then again, I'm going to talk more about this, but in a later paper that was motivated by a question of John Steele, we show that the following prove the same pi13 statement. So they are conservative for pi13 statements. Well, these two we said already, second arithmetic. And then this is the scheme. Every Boolean combinations of n pi03 is determined for all the n's. So they prove exactly the same thing. So it's kind of like a reversal of a reversal. Like we're doing a reverse, have C2 and we're trying to reverse C2 to a determinacy statement. And then that's kind of like a very sharp answer in there. Okay, so I'll mention more about that, more details on that in a bit. Okay, so how is that we deal? We're not really dealing with Boolean combinations, like just in general. I'm putting that just to make the statements easier before putting the definitions. What we're actually dealing with is
514. 514.
514.
Can you go back to the theorem?
Yeah.
The following prove the same 513 statement, right? And what if we replace the 3 with 4 over there?
I don't know. I was thinking about that on the plane the other day. I prepared this talk well this past week. I don't know if it works with 514.
Yeah, I just wanted to know if this is something that you know that doesn't go through, or you don't know yet whether it goes
I think it doesn't, but I don't know, right? So in the previous look, so between these two is 514.
Mm-hmm.
But this one I think is 514. But yes, I was just thinking about it then. I'll tell you why 513 works and then. Okay, so how is that we deal with the Boolean combinations? We're actually dealing with the difference hierarchy instead of Boolean combinations. So we say that a set A is M pi03 and the M is for difference of M sets. If there are pi03 sets, A1 up to AM, which are nested, such that A can be written as A0 minus A1 union A2 minus A3 minus, and so on and so forth. So you're adding, subtracting. That's a different hierarchy. That's kind of like Kuratowski or Eschoff hierarchy. So it's a difference of M pi03 sets. Equivalent way of writing the same thing. It's a decreasing sequence, so every real is going to stop belonging to a sequence somewhere along the way between 0 and M. If that first I that you don't belong to is odd, then you say you are in the set. If it's even, then you are. And you can this is not too hard to show, but it's an exercise like this. Boolean combinations of pi03 sets is exactly the same as the union of these M pi03s. So every Boolean combination is M pi03 for some M, and vice versa. And that union is called omega pi03. This idea could be extended to the transfinite. Like this is just the omega case when you have finite sequences, but if you had a transfinite sequence going down, you could use that third line up there as the definition of your set, and you could have like alpha, something in the alpha difference hierarchy of pi03. And Kuratowski showed that if you go through all ordinals, then you get to the next. Okay, this is a typo. This is k plus 1. You go to the next delta. Delta k plus 1 is the union of all the alpha differences. And that's what Martin was using to his proof of delta for determinacy. He was using difference hierarchy for pi. So the Boolean combinations are only the beginning of this hierarchy, getting to delta 4. Okay, so essentially the question we are looking at is the strengths of n pi 0 3 determinants. That's the class that we are looking at. Difference hierarchy of n pi 0 3 determinants. So what is, so in more detail, I'm gonna, the results that I gave before, I just give them in a bit more detail. What we prove, following Martin's proof, but just being very careful about the reverse mathematics uses of the axioms you're using, is that to prove n pi 3 determinacy, you need, well, it's enough to have comprehension for pi 1 n plus 2 formulas, but delta 1 n plus 2 comprehension is not enough. And that's kind of like the key here. So that stratifies this n pi 3 determinant right there. The case n equals 1 was proved by Welch, Peter Welch, before. And then, right, the corollary is what I wrote before, that C2 proves that for a fixed n, but not for every n. All right, so we count that, okay, so this is the result. You can prove it from this, you cannot prove it from that. So that tells you that it's somewhere in between. The next question is, can you get reversals? This is not a reversal, this is just not provable in. So Metzamer and Tanaka, they had already shown that even Borel determinacy cannot give you delta 1 2 comprehension from pi 1 1 comprehension. I guess it's a matter of the complexity of, but determinacy is pi 1 3, so it's not going to prove any interesting pi 1 4 statement. So they had showed that. So there is no, essentially there is no reversal possible from anything weaker than Borel determinacy to something like a beyond delta 1 2 comprehension. But then, right, so actually we show something that even further. We show that whenever you have a sigma 1 4 sentence that is true, the sigma 1 4 sentence is not going to allow you to go from pi 1 n comprehension to delta n plus 1 comprehension. And it's not going to allow you to go, it's not going to let you go from delta n to pi 1 n comprehension. So all those jumps you need more than sigma 1 4 sentences. So there is no hope for reversals. So I was giving this talk and John Steele then asked whether we can get reversals for consistency. So then we got together again with Richard and started looking at that question. And okay, that's what I said before. Then we do get the reversals for consistency. And we get that in that case, yes, determinacy is at the level that it should be from the picture before. So n pi 3 determinacy in terms of consistency is strictly in between those two comprehension schemes, delta n plus 1 comprehension and delta pi n plus 2 comprehension. So it's exactly there in between, and it's actually strictly in between. So how is that we look at the consistency? We actually look at something stronger than consistency. Okay, but I forgot to say this. Omega pi 3 determinacy is consistency-wise stronger than full second arithmetic. Okay, how do we look at consistency? We look at something that is a bit stronger than consistency. I guess beta, I don't know if beta consistency is a word. Well, this is what I mean. So a beta model is a well-known notion. A beta model is an omega model of second order arithmetic where all sigma 1 1 formulas are absolute, in the sense all sigma 1 formulas that are true in the model are true in the real world and vice versa. So they are, first order part is omega is the right thing, and whatever the model thinks about sigma 1 statement is also correct. So we define this statement. So given a theory T, we define this notation. Beta T is a statement that says every real x belongs to a beta. For every real x, there is a beta model of T containing x. And by the beta model here, I mean a countable beta model. So it's just given by a sequence of reals. So it's a single real coding the whole beta model. That it's absolute for sigma 1 formulas. So beta T is much stronger than consistency T. Consistency T is equivalent to the resista model. This says that there exists a beta model, so it's much stronger than just saying that there is a model. I guess it was Harvey who showed. So any beta model is just, for being a beta model, it's a model of AT or not. So if you have a beta model of RCA not or nothing, for free you get AT or not. And just the existence of a beta model is equivalent to pi 1 comprehension. So when you're working with beta models, you're working at least with pi 1 comprehension or beyond. So beta models give you this thing. So if you have a theory S that proves beta of T, the one what you can get from that is that the pi 1/3 consequences of S contain the pi 1/3 consequences of T. Okay. Do I want to go into this little proof? Maybe not. No. I mean, there is nothing to this proof. If suppose you have a pi 1/3 sentence here that is not there, take a model of S which doesn't satisfy it, take the witness, build a beta model that contains the witness to satisfy T, so to satisfy the other one. You play around with that, it's very easy to figure out that proof. There is nothing there. So okay, so that's how we're gonna get the thing about pi 1/3 conservativity. You prove the beta of something.
Is there anything essential about beta models in this sketch of proof?
Yes, so at some point you have these two models. One is a beta submodel of M, and one is satisfying pi formula, and the other one the other one.
Thank you.
And the beta model should satisfy the same formula, so that's how you get the contradiction. In the case of the pi 1/4 conservativity we mentioned before, actually you had models of full L. This was all of L in the other one. And in that case, you have Schoenfeld absoluteness, and you have pi 1/2 absoluteness, but that's how we get pi 1/4 between Z2 and C of C minus. But here with beta model, which is 125. That you get there at the end. Okay, so that's how we're going to be playing with consistency. You're going to use this notion of beta consistency. There exists a beta model of T. And this is the precise theorem that we got in the second paper. We had to improve the techniques, and this is what we get. This is sharper than what we mentioned before. So the strength of n pi 3 determinacy, so it's implied by pi 1n plus 2 comprehension, and it implies, so before we just said that this one doesn't imply, that delta n plus 2 comprehension doesn't imply this one. So here we improve it to say that it implies beta of delta n plus 2 comprehension. And this is stronger than consistency. So if it implies it, then this one cannot imply it back, I guess. So this one doesn't imply that. So that puts n determinacy better in there. If you put a chain of all the beta statements for the comprehension system, this is right in between those two, and it's strictly between. And these are all pi 1/3 statements, by the way. The beta of something, beta T, and determinacy. These are also a sequence of pi 1/3 statements. So it makes sense that this spine of determinacy statements lives among the beta statements, because they're all pi 1/3. And that's how, with the corollary of this, the theorem that I mentioned before, is that C2 proves the same pi13 statements as every Boolean combination, right? And pi3 statements is determined. So if instead of working with second order, you want to work with determinacy, this is kind of what you want to work, and you don't need to go comprehension on a very high formula, very complicated formula. Okay, so about the techniques. So let me spend a little bit on the techniques. Okay, so I'm not gonna, the proof is complicated, it's very complicated. But at least I give you a little bit of the ideas that go in kind of this, so you see kind of what sort of proof it is. But it's gonna be very far from giving any detail at all, because that's quite, it is quite technical. So first, a connected question to finding the strengths of determinacy in second order arithmetic. Question that is connected to that is to ask, so given gamma, instead of asking how hard is gamma determinacy, how far in Gödel's L hierarchy do you need to go? How far in L do you need to go before you find the strategies for all gamma games? So what is the ordinal that you need to so that L beta has the strategies that you need? That's a question. Okay, that's what I just said. What is the least ordinal gamma such that L gamma satisfies gamma determinacy? So that's a connected question, and that's kind of the way it's usually these questions are usually looked at when you go beyond at least beyond pi03 determinacy. That's the techniques you use. Harvey, so the result that he showed about power set axioms is essentially this. I guess the 4, I guess it's Martin got that 4. So the least ordinal gamma such that L gamma proves pi4 plus beta determinacy is greater than or equal, though very close to what Martin showed later, to the least ordinal gamma such that L gamma shows satisfies CFC minus, plus there are beta iterates of the power set axiom. That's kind of what he shows. To prove this much determinacy, you need beta iterates of the power set axiom. So what are the ingredients? Let's just call it that, the ingredients that show up in our proof. So we need to use this admissible theory that was popular in recursion theory in the 70s, and Richard was definitely an expert, is an expert. So we say that an ordinal alpha is inadmissible if it satisfies one of the following equivalent statements. So these are all equivalent definitions. So one is that L alpha satisfies sigma n minus 1 comprehension and delta n minus 1 replacement. Some versions of, some weakening of CFC. Yeah.
That should be an N. That should be an N, right?
Yes, thank you. Yeah, yeah. The M and sorry, the M and the N should be the same. Yes, and I guess not power. Yeah, no power. Another definition is that there is in L alpha there is no function that is sigma n definable in L alpha from a smaller ordinal to alpha that is cofinal. So in L alpha, alpha looks like uncountable if you consider only sigma n formulas. You cannot reach it from below. It's some form of regularity. You cannot reach it from below. From an axiom that is from a ordinal that is below alpha.
What's the quantification of delta? Oh, just smaller than alpha.
Yes, for any delta that is smaller than alpha. Okay, so these are called the inadmissible. If you have an inadmissible ordinal alpha, then L alpha satisfies delta n plus 1 comprehension. Well, the reals in L alpha satisfy delta n plus 1 comprehension. So that's the model that we're going to be looking at. So if we call alpha n the least inadmissible ordinal, then we have a model of delta n plus 1 comprehension. One observation is that the theory of L alpha n doesn't belong to L alpha n, because the theory of a structure cannot be defined within the structure, and in L alpha n everybody is definable and something. So this is a real that doesn't belong there, and what we need to do, kind of the key lemma, that is what the whole proof is that we need to find a game of the right complexity where the players are playing sets of sentences. So they're playing yes or no to sentences of set theory, and they end up building theories, one theory each of set theory. And we need to do it in a way so that actually one plays a theory of L alpha n, she wins. And if one doesn't, but two does, then two wins. So whoever plays a theory of alpha n wins. And we're going to have that if this is true, then a winning strategy for this game must compute theory of L alpha n. But theory of L alpha n cannot belong to L alpha n. So this game will not be determined in L alpha n. So we're going to have that L alpha n is a model of this, but not of that amount of determinacy. And the hard part of the proof is how to decide who's playing the theory that is closer to theory of alpha n in a statement of this form, in a game of this form. Because you have very restricted complexity, and you're given two theories, and theory of alpha n is way high up in complexity. But you don't need to decide who's playing theory of alpha n. You just need to decide who's playing the better theory. You just have to compare the two. They are building theories. You get models from the theories, and now who's playing the better model. So that idea of building the models from the theories and playing this theory of L some ordinal, that appeared in Friedman's proof that sigma phi determinacy wasn't provable in second order arithmetic. In his proof, he doesn't use inadmissibles. He used the least ordinals, such as L beta satisfies essentially CFC minus. So it's another ordinal, and he's allowed to use a sigma phi or game, which gives you much more room. So here we have to be very precise on how to describe the game, and we have to use some higher recursion theory because we're using this inadmissible to get this precise bound. Okay, so that's what happens in there. I guess I'm running out of time. Okay, for the second theorem had to, I'm not gonna go into this. We had to modify the games. And essentially, what we need to do now, instead of showing, before we show that L alpha n doesn't prove certain determinacy, now we need to show that determinacy of the right kind proves that the ordinal exists. So it's like a different type of proof that has to change. So instead of showing that we couldn't determinacy didn't hold, now we want to prove that the ordinal exists. And then once we get that the ordinal exists, then we build L of that ordinal, and that gives us a beta model of delta n plus 1 comprehension. Because if that's an actual ordinal, then this is a beta model. And so that's how we get the beta models of delta n plus 1. Okay, I can give you a bit more of ideas, but I'm going to skip this because I have time. So this is a question that I was thinking about recently. Maybe I'm just going to throw the question out there. I asked it to a couple of people, and nobody knew the answer. I don't know if anybody here has seen this question before. So we had the pi 1-3 consequence of CFC minus. They were the same as second arithmetic, and they were the same on determinacy up to that level that I mentioned. If CFC by itself, well, it's the accepted axiomatization for mathematics for the last 120 years. So it's supposed to be natural. So the set of second order consequences should be somewhat natural also, I would guess, I don't know. Or maybe pi 1-3 just to make it simpler. So what are they in the sense of, can one find like a nice second order theory or set of second order statements that prove the same 513?
Is it decidable?
Huh?
Is it decidable?
Is CE. It's definitely not decidable. Well, maybe the list of axioms could be decidable.
That's the lowest level of the hierarchy, that there is even a sense of asking a question due to Schoenfeld's absoluteness, right?
Well, I mean, if there's a CE list of,
Right, yeah, okay, so, yeah.
there's a CE list of axioms, there's a computer list of axioms.
Yeah, I mean, you could list them with a computer, just list all the consequences.
Yeah.
But okay, so the question, right, so it's ill posed. I mean, what I really mean is where you can find something that you can see the meaning, like in the case of, okay, these determinacy axioms, or something that you can see what the consequences are. For instance, this is an actual statement where you get something like this is like, well, one of the most beautiful results of that came out of the work in Wooding and Martin and Steele. The following two have exactly the same second order consequences. Like all second order statements that they prove are the same. One is CFC plus there are infinitely many Wooding cardinals. And the other one is RCA not with projective determinants. So this is a second order theory. The first one I write as a scheme there, it's not minor. So when I say infinitely many, I say you have the axiom there are n many, and then you put that for every n a different axiom. They prove the same thing. So in a sense, it's like if you don't like things that are uncountable, you can work with this one. But then if you ask, okay, why is it true? Well, this because that.
So is DSC plus their infinitely many Witten cardinals conservative over ZFC for pi3 sentences?
No.
Is it no?
It
For
proves projective determinacy.
Hmm?
It proves projective determinacy, which is not true in ZFC.
Okay.
Yeah.
Yeah, it's not even pi 0
Right, it proves the consistency. It proves the consistency of DFC.
It proves the consistency of DFC.
And other results. Okay, these are all. I wrote this in the plane, so I don't know if it's what the exact results are, but they're almost. But just to give you the idea of like the context of the first question, from the results of Martin and Friedman, you can see that the following have almost the same 513 consequences. One is CFC, but only with countable replacement. This is not exactly correct. That's why I'm saying not exactly correct, but just to simplify it. So, and Borel determinacy, which is a second order statement. This is 513 theory right here. It's not countable replacement. It's not exactly the same thing. But it gives you it gets very close. What is exact state? I don't know if anybody looked at something. Again, a sharp result here, but that would be interesting too. I mean, Harvey's Borel determinacy, you need for every countable alpha, you need alpha iteration of the power set. So the model for that is essentially you do one iterations of the power set, and that's exactly what you get with countable replacement. You go all the way, you do power sets up to, you get the same kind of models, and then so they should be very close, but not the same. And if you do finite replacement, then this is same as arithmetic determinacy. So pi 0 n determinacy for all n. Those are very close. But CFC seems to be in between these two. So where is it, CFC? That's one question that I'm proposing. This is just another. This is just again, I was preparing this in the plane. It's another statement that is in between these two. That I don't know what the answer is, but that's from a different talk. Somewhere in between is the second order statement that says every x computes a structure that for every x there is a countable structure that computes x and a copy of its own jump. That's somewhere in between these two in terms of pi1,3 consequences. I don't know where. Well, I think the first question is the more interesting one. All right, thank you for your attention.
Okay, thank you very much. So is there any question?
Let's
So
say
yes,
Laura,
there's a here. So Harvey has questions.
So long as it's not about strict reverse math, because he's gonna talk about it later.
So, now, Harvey is supposed to have the right to talk now.
Do I need to?
Yeah, but let me see somebody. I mean, let people see me.
Well, you're not going to be visible anyway because nobody is visible right now in the room.
Oh, okay. All right. The question is, what if you do all this for Turing degree determinacy?
Oh yes, okay, so we do that for Turing degree determinacy. You mean So we look at that, and we get that. Okay, I had to remember what the results were. I think sigma 5 is not provable in second order, and then when you go to sigma 4, we can prove them in second order, and they are at the level of, I don't remember, pi1,3 comprehension, and then we do find the different levels of Turing determinacy within second order in a different paper. It's the spine that we get is not as fine as this one for Turing determinacy. Still interesting, and then the techniques are very different, so which makes them quite interesting because we need to build models where you have Turing degrees that avoid combs.
Oh, that's interesting. So it really is a different. So it really has a lot of different techniques.
Yeah, we have to use kind of results from the structure of the Turing degrees to find things where, like.
Is that also you did that? Is that you did that also with Richard?
Yeah. So that's a different paper that we did with Richard. Yeah. Yeah.
I just wanted to know what are some theorems of regular, say, real analysis that are at the pi1,4 or pi1,5 level? Like, is this normal mathematics?
No. So that's another reason why it's almost the same to look at CFC minus and C2. Yeah. I mean, I'm sure somebody knows some example, but then there are very few examples of something at that level.
Metrizability for MF spaces is a pi1,4, I think, but that's barely real analysis.
Right.
Sorry, what was that?
The metrizability theorem for MF spaces, I think, is pi1,4. It implies pi1,2 comprehension, so it has to be pretty high.
Right. So in that sense, like the pi1,3 there is not a big restriction on the question in that sense. So it's kind of the interesting stuff are pi1,3 or a good fragment, very good fragment.
Okay. Any other questions? Yes.
Yeah, so when you had the case where there was like you had to keep adding more axioms for larger n, and then eventually you get infinitely many, which axioms do you have to add?
The more and more comprehension. Okay, let me show you. So I said that, and then, okay, so here is, I know. Right, to prove n pi3 determinacy, this was enough. But as n goes up, then you need more and more comprehension. Yeah.
Okay, no more question? The chat? No? Okay, so let's thank the speaker again.